Swayam Prabha. Digital India. Educated India.
Now, in the remaining few minutes, what I want to do is, I want to find out how the bonding between steel and wood have to be. Okay, how the bonding between steel and wood have to be to ensure that they act integrally. Okay, so say I add, this is designing the connection between steel and wood. Okay, so I add the cross section in here, which is steel and wood. So now say, let us say I nail through the steel and I penetrate through the wood like this. Okay, this is the cross section. Now in the elevation, or this is in the y z plane, if I look from bottom, what will happen is I will have the steel plate with some screws on it at equal distances apart. Screws or nails nailed onto it at some equal distances apart. Okay. Now let us say the spacing of this nails is S. Okay. What am I interested is, what should the spacing be, so that what is the spacing, so that I can get an integral action between the steel and the wood. That is, I do not want, we saw the shear stresses develop in the beam to maintain the integral action. If the steel and the wood were to deform differently, then what will happen is, there will not be this integral action between steel and the wood. The wood will deform, there will be top surface will be in compression for the wood, bottom surface will be in tension for the wood, and the steel also will have top surface in compression, bottom surface in tension, and there will be a separation at the interface between the steel and the wood. That is not what we want, right. So how do you connect, how do you design this connection is the question. Okay. Now for that you have to find the shear stresses that will come at the steel wood interface. Okay. So we saw that the shear stresses sigma xy is given by V into ys as divided by izz into b, right. Now we derive this expression for a homogeneous section, wherein we said that sigma xx is given by m by mz by izz into y minus y naught. Okay, this is what we used the expression for the bending normal stress. Now what will be the expression? Sigma xx would be Ey times y minus y naught mz, that should be a negative sign here, divided by integral Ey y minus y naught whole square dAx, Ax with the negative sign, right. Okay. Now looking at the magnitude, is how the magnitude of the actual bending stress would be. Okay. Now what I was interested was d sigma xx by dx is what gave us this Vy here, right. So that will still be minus E of y minus y naught divided by integral E of y minus y naught whole square dAx into dmz by dx, that will be minus Vy, which will mean that this will be Ey times y minus y naught Vy divided by integral E of y minus y naught whole square dAx. Okay. Now that is d sigma xx by dx. Okay. So now either I have to do it like this, wherein I have to go from first principles and rewrite the sigma xy expression as Vy divided by integral E of y minus y naught whole square dAx b of y no, into B into integral y minus y naught dAx E of y dAx up to the section where I am interested in finding the shear stress, okay, from y to d by 2 say up to an or dAx section, that is up to, if I am interested in the shear stress at this location, this will be dAxs, okay. So that is how this is from the first principles. On the other hand, if I use the equivalent section approach, then I need not change this expression for shear stress, it will remain the same, except that now I have to use this as the cross section of this beam, this as the cross section of the beam, wherein this will be m times b, this is b, this is d, and this is t, and my expression for sigma x y remains as Vy into Ys into As divided by Izz of this section times B of that section, okay. So now then the problem boils down to the same thing as before, okay. You have a section, you can find y s As for that up to this point, you have to find y s As up for this entire region, okay, for that entire region, and then you have to find what is the tributary area of this nail. The tributary area of this nail would be the width of the cross section times s, wherein this is s by 2, this is s by 2 and this is s by 2, okay, and you have to multiply this sigma xy with s by s times b, and you have to equate it to the nail allowable shear force in the nail, okay. So sigma xy then would be Vy into that entire area is BD into the center of that cross section would be measured from the neutral axis, Ys should be measured from the neutral axis. So it will be neutral axis is somewhere here, this is the neutral axis, the center of that cross section would be this distance is d by 2, and I know that this distance is y naught. So I am interested in this distance, that distance would be d by 2 plus t minus y naught, okay. So this will be d by 2 plus t minus y naught divided by Izz is for this section would be the expression given in here, Izz for this cross section would be this expression in here with E of foot as the Young's modulus, this will be the effective moment of inertia of that, okay. So divided by Izz into B is, I am looking at the wood interface, so I have to look at the shorter region, so it will be B, okay. This into S into B must be the shear force allowable in the nail. So once we know this, you can rearrange to find B, okay. That is how you solve this problem, okay. So that is it for today's class. What you have looked at is how do you analyze inhomogeneous beam, how do you find the axial stresses, how do you find the shear stresses, and how do you analyze for the deflection of the beam, okay. The basic equation is, basically there are two approaches. One is you can modify the basic equations to get these expressions for y naught and the bending equation, or you can transform the cross section by using a modular ratio times the corresponding width of the cross section when the variation in the cross section is only along the one direction, y direction, okay. Then you can do this modular ratio approach, whereas this bending equation are general when the variation in the cross section of the properties is both in the y and z directions, okay. Thank you.